Any question? I'm really.
Yeah, we have a question. Constantino.
Mohsen, fantastic presentation. Thank you very much. I have a curiosity about the submitted paper that you spoke about, the one where you electrically tuned with, it seemed to me 0.6 milliseconds, something like this. Can you tell us something about the electrical contact? They were locally, you said. I could not understand precisely how are
that paper. Actually, it's something that I really love. It's like a baby. We have been working on that for many years, and I'm really proud and excited about that paper. So yes, so what happened? So we have the metasurface, and we have done a lot of different efforts to find the best combination, but we realized that the best candidate is the membrane metasurface for some reason, which are written in the paper. So, but we have this membrane metasurface, which is the silicon film with the holes. Then we have the ITO on the top. This ITO is a heater. So what happens? We have this. We have connected this two side of this heater to our electrodes. So then we bias the voltage. So this voltage, because ITO has some resistance, and that resistance also can be controlled by annealing when you fabricate the device. So, but still there are some resistance inside the ITO. So when you apply the bias of voltage, so you heat up the ITO, but because it is transparent, it doesn't really change the optical properties much of your metasurface, but it's changed the refractive index of your metasurface. So then you will see those shifts, then you will see that tuning. So okay. What happens, it is true, 0.6 millisecond is what we achieved for tuning, which is really groundbreaking. Sorry for advertising it, because I'm very proud of that.
No, thank you very much. So it's based on the temperature increase of the lattice, not on the carrier concentration induced by injection.
No. Yes, that's right. That's
okay.
right.
Thank you very much. Amazing.
Temperature
0.6
of the lattice.
milliseconds.
Temperature of, yes, that's true.
Amazing. Thank you very much.
Thank you so much. But it is heating. It is heating down. And the cooling is a little bit. It is a little bit slower, but because it is the first paper, it's in its kind. So that's why we didn't really put effort on different strategies for cooling. There are a lot of other ways to enhance the cooling speed, so which we are working at the moment, but we wanted to report it that even for heating, just heating it up, you can achieve 0.6 millisecond.
Thank you.
Thank you. Do we have more questions from the audience? Just unmute yourself, please, and ask the question if you have any. I have actually a few questions.
Sure.
So my first one is about the liquid crystals, something that we are actually interested in acoustics, in mechanics, in particular for this possibility of reacting fast. And I was wondering if in optics here, if you have tried to use liquid crystals in the liquid form to try to change their effective optical property with an additional laser or something like this.
I personally didn't, but I showed one of work which was, as I mentioned, by my colleagues with Andrei Komar, Dragomir Neshev, Isabel Stout. So they did it actually. They had the metasurface at the bottom, then they had the liquid crystals on the top. So by applying the voltage on the liquid crystal, of course, you can change the direction of those liquid the cells. Then in total, it changed the optical properties of your device, because the optical properties of the metasurface is constant, but by changing by applying voltage in the liquid crystal, so you are changing the environment indeed. Then what happens? So you will get the total change in the total device. So in the optical properties of device. Yes, it is a nice research direction undergoing by some of my colleagues by merging liquid crystals and metasurfaces.
Okay, thanks. Do we have more questions from the others? Actually, I have two other questions that I was just waiting at the end to ask them. So the question is very simple from the theoretical point of view. What would be if someone would give you the possibility of picking up any particle, dielectric or metal, with the properties that you would like to have, what would be the best one for sensing? What would be the best metallic particle for sensing and the best dielectric one? Giving the possibility that you can, of course, select the losses that you wish or eventually gain that you would like to have.
This really depends. And as I was trying to cover it in my talk, it really depends on what is your application. Sensing can be sensing a lot of things. Sensing can be sensing DNA, can be sensing proteins or viruses, or can be sensing maybe oil and some other materials. So sensing can be very different. So it's really dependent that what material you are going to sense and what is their sensitivity to different things. For example, whether your material or cell or molecules is sensitive to heat. If it is very sensitive to heat, probably plasmonics is not good for you, you know, or maybe just your material is super small and it changed very, very small change in the refractive index. And then in this case, probably you have to go for plasmonics nanostructures. So it's very dependent on what you want to send. That's why my conclusion is that hopefully now we are in the position that machine learning can just get all of this information and just consider the advantage of each of these platform, plasmonics and dielectrics, and tell us that if we want to do it for very, very particular application, like as you mentioned, sensing of very particular substance, then the machine learning can tell us which one is the best.
Thanks. Actually, I had in mind a particular sensing. What about the possibility of using the optics for gravitational detection of gravitational waves? Is there a hope, or it's no way? We are probably orders of magnitude far away from that.
To be honest, I don't want to give you wrong answer, so I prefer to not answer that, because if I tell yes or no, there may be some advocates for each part and they said that no, it's wrong. It is again also a subject of debate. So that's why, if you don't mind, I keep that question open. So for the following discussions, because there is again not a black and white answer.
Okay, thanks. Just checking at the public if there is any other question. Apparently not. They are rather shy. So I would like to tell you thank you again from the MetaMAT, from us. Your talk have been recorded. It will be made available soon on the platform, and a DOI will be assigned to it in a way that anyone willing to cite it in the paper, or if you wish to cite it, it's possible. So you will.
Thank you so much.
It will be made available permanently.
Thank you so much. I appreciate that.
So thank you very much for.
Thank you.
Thank
you for having me here.
Thanks.
Thank you. Bye.
Bye.
Bye, everyone. I'll stop the record now.